Hi, everyone. So for today, I wanted to walk through the trig identities that we saw on the skills check last class, and I'm going to walk through all for problems on both versions. So I'm going to work through, you can see here, I'm going to work through the first page, version 1, version 2, and then the second page, version 1, version 2. You'll notice that problem number 4 is the same for both of us, regardless of the version we had. But since you have these and if you want to see them done properly, I will walk through those now. All right, so let's start with version 1, number 1. Sorry, this is the wrong one. Version 1, number 1. So on this problem, I would recommend working on the left-hand side, but I'll demonstrate what we could do on the right-hand side, and hopefully we'll see why that is maybe not the best decision that we can make. So I'm just in black here. I'm going to work through on the left-hand side. So why would I work on the left-hand side? I have a sum compared to a product. And generally speaking, when we have a sum, there's more we can do with it, right? We can reorganize things differently. So my first step on the left-hand side would be to rewrite tangent x as sine x divided by cosine x, and cotangent as cosine x divided by sine x. And while it doesn't necessarily get us exactly where we're going, there's some hints that this is a good idea. Dividing by cosine is reminding me of secant. Dividing by sine is reminding me of cosecant. Let's see if we can get there. Well, now I have two fractions that I'm going to add together, and the way I'm going to do that is by creating a common denominator. The way that common denominator is being created is we're multiplying the left-hand term by sine x over sine x, and the right-hand term by cosine x over cosine x. Why is this legal? All we've really done is we've multiplied each expression by the number 1, and when we multiply by 1, we don't change its value. So what we're left with here is sine squared x plus cosine squared x in the numerator. And I hopefully at this point, we're feeling that we are a little bit more comfortable with an expression like this, and that sine squared and cosine squared is going to turn into 1 over the cosine x times sine x. Now we could split this into two separate expressions, but what I see here is that this numerator is really 1 times 1, that denominator cosine x times sine x, and when we separate those out, 1 over cosine x is secant x, and 1 over sine x is cosecant x. That's where we were headed. Now, say we started in a different direction here. I'm going to just separate this. And we started working on the right-hand side. What we could do is we could write this as 1 over cosine x times 1 over sine x. And where we'd want the big leap we'd have to make, right, when we combine this to a single fraction, the big leap we'd have to make is we'd have to rewrite 1 as sine squared x plus cosine squared x, all over cosine x sine x. And that's a strange step. Personally, it doesn't jump off the page at me that 1 is the same as sine squared x plus cosine squared x. I think that's a good way to see why we really prefer to work with sums as opposed to differences. From here, we'd want to split up our fraction. Sine squared x over cosine x times sine x, and cosine squared x over that same denominator, cosine x sine x. And you can kind of feel that we're basically doing what we did the first time around in reverse. We can simplify each of these fractions, and what we'd be left with is sine x over cosine x plus cosine x over sine x. And as we know, that is tangent x plus cotangent x, and that's where we were hoping to go. So that's the first one. I'm going to try to work through the next ones a little bit more quickly. I think the next one really gets us into trouble if we try to work on on the right-hand side, so I think I'm even going to shy away from demoing that. So what could I do on number 2? What makes me choose the left-hand side as opposed to the right-hand side? There's more going on here, right? When I have a binomial that I can expand, I'm going to create quadratic or second degree expressions here, and that allows me to open up some of our Pythagorean identities. If we wanted to go the other way, we'd have to end by factoring into this form, which is just a little bit trickier and a little bit complicated. So what I would do on number 2, again, this is number 2 on version 1, is I would expand out this left-hand side, and I would get tangent squared x plus 2 tangent x cotangent x plus cotangent squared x. And you know, at this point, I have a good feeling about my quadratic terms, right, my second degree terms, but I don't quite know what to do with this middle term, right? That middle term, that tan x cotangent x, is strange, but what I do remember is that tangent and cotangent are reciprocals. And when I multiply a reciprocal by itself, I get 1 as a result. So my next step, I want to keep that in the same color. My next step here is going to be tangent squared x plus 2 plus cotangent squared x. And I know that I'm headed towards cosecant squared and secant squared. What I have in the back of my head are my Pythagorean identities. So I know that tangent squared plus 1 is secant squared, and cotangent squared plus 1 is cosecant squared. So if I were to split up this 1, I've created 2 different Pythagorean identities. Tangent squared plus 1 is secant squared x, and 1 plus cotangent squared is cosecant squared x. Well, that's where we were headed from the start. I'm going to keep working through this first page, so the next 2 problems we'll see will be from version 2, examples 1 and 2. On this example, I think that it's very clear that the left-hand side is more complicated than the right, right? Not only are there fractions, but those fractions are being added. While this looks a little bit messier as we look at this, what I like about it is that it immediately gives me an option on where to go. So my first step is going to be to create a common denominator. And the way I'm going to do that is I'm going to multiply the left-hand expression by sine A over sine A, and the right-hand expression by 1 plus cosine A times divided by 1 plus cosine A. So in my numerator on the left, I will have sine squared A, and then in my numerator on the right, I'm going to have cosine A plus cosine squared A. Hopefully by now, those sine squared and cosine squared rings a bell a little bit, that's a Pythagorean identity. And in the numerator, I should have 1 plus cosine A divided by the quantity 1 plus cosine A times sine A. Now, I don't know if you caught it, but I did do something along the way that you maybe didn't see on screen. In the numerator, right, I was multiplying this times 1 plus cosine A and 1 plus cosine A in the denominator. Now, I can always distribute in the denominator, so I'm hoping that I should be able to cancel anything that's not sine A in the denominator. So the reason that I distributed in the numerator, right? When I multiplied these together, I distributed that cosine. But I didn't distribute when I was multiplying my denominator together. Why might I have made that decision? Well, the reason I would make that decision is because ultimately I am headed towards the cosecant A. And I know cosecant A can be rewritten as 1 over the sine of A. So I like having this sign in my denominator. I don't want to muddy it up with that cosine A. And now we can see in our final step here that what emerged as part of the numerator was the same as the factor that I was hoping canceled in the denominator. So when I cancel, I get 1 over sine A, which we know is the cosecant of A, and we're done. On number 2, this is another problem here where I really recommend against working on the right-hand side. We're going to have to create a 4th degree. We're going to have to introduce multiplication into the problem at some point. And to me, I think that's just more complicated than it's worth. What we want to focus on here is factoring the left-hand side, right? Even degree exponents here and a difference in the middle. So what we are going to do is use our difference of squares factoring. Oh, sorry. So that'll be secant squared n plus tangent squared n times secant squared n minus tangent squared n. And maybe we don't remember them perfectly, but the Pythagorean identity involving secant squared and tangent squared is there on the right-hand side of the screen. Well, if I were to manipulate this, if I were to subtract tangent squared from both sides, I would create secant squared x minus tangent squared x. Well, that's just exactly what I see, right? This here can be seen in our problem with that second set of parentheses. In other words, secant squared n plus tangent squared n is being multiplied times 1. So there is where we move from a 4th degree to a 2nd degree problem. And then I'm going to use the original identity that you see up here to get rid of my secant squared expression. So I'm going to have 1 plus tangent squared n plus tangent squared n. And what we can see there, when we combine those like terms, we create 1 plus 2 tangent squared n. That is where we are headed, and there's our identities. All right, so we're going to look at the problems on the back side of this page. These ones will go a little bit quicker, right? There's a little bit more creativity and outside-the-box thinking that we have to do with verify problems. When we get to the back side of these skills checks, we get a little bit more straightforward use of formulas. All right, so number 3 on each problem was a sine or cosine sum or difference. There's a couple ways we could approach this. We will get the same answer however we do this. When I did this problem, I rewrote the sine of 165 as the sine of, 135 plus 30. And then using my sine sum formula, I'm going to get the sine of 135 times the cosine of 30 plus the sine of 30 times the cosine of 135. These are all values from the unit circle, so I'm going to evaluate them now. The sine of 135, that's a 45-degree reference angle in quadrant 2. Sine is positive there, so we're going to get root 2 over 2. The cosine of 30 is going to get us root 3 over 2. And cosine's positive in the first quadrant. The sine of 30 we know is 1/2, and the cosine of 135, that's going to be negative root 2 over 2, because 135 is in the second quadrant, and that's where cosine is negative. So we simplify our fractions here. We're going to get root 6 minus root 2 all over 4, and there is our answer. I'm going to jump down to example 3 on version 2 now and walk through a cosine problem just so you can see how this would work if you didn't quite get it. Again, we could use different values here. I'm going to use, let's do 120 and 45, right? There's not always just a single path through these problems. So on this one, I'm now using the cosine sum formula, the sum formula, which is going to lead me to cosine of 120 times the cosine of 45 minus the sine of 120 times the sine of 45. The cosine of 120 degrees is going to be negative, and it's going to be negative 1/2. The cosine of positive 45 degrees, root 2 over 2. I'm going to subtract from that the product of the sine of 120. That's going to be root 3 over 2. And the sine of 45, root 2 over 2. So as a final answer here, we will get negative root 2 minus root 6 all over 4. There's our simplified answer. And then finally, on the last problem, I'm hoping that when you saw this, these angles raised your eyebrows a little bit, right? Those are strange angles that we don't work with quite a bit. What I'm hoping you realized is that this is the same as our tangent sum and difference formula. So we could condense this down pretty significantly, and we can see here that 2 plus 28 is 30. So what this whole big ugly expression is really telling me is to find the tangent of 30 degrees. Well, that's, again, a unit circle value. I saw somebody wrote their work like this, and I kind of liked it. Right? Maybe we don't think as clearly about tangent on the unit circle, but we can use our quotient identity. And what that will be is 1/2 over root 3 over 2, which is 1 over root 3. And when we rationalize, root 3 over 3. All right, guys, hopefully this makes a little bit more sense on these problems. Thanks for your time.